Acids and bases, we see them everywhere in labs, in industries, and even in the products we use daily. But have you ever wondered how they're actually made? Whether it's a small scale preparation in the laboratory or a massive industrial operation, the methods are carefully chosen based on their reactivity, volatility, and chemical nature. Acids might be prepared from salts, from oxides, or by direct synthesis, while bases often come from oxides, carbonates, or even through clever displacement reactions. Let's explore exactly how these methods work. First up, hydrochloric acid, one of the most common laboratory acids. The process is simple but effective. We react dry sodium chloride with concentrated sulfuric acid. This produces hydrogen chloride gas, which we collect and then dissolve in water. The equation goes sodium chloride plus sulfuric acid gives sodium hydrogen sulfate plus hydrogen chloride gas. Because this gas is heavier than air, we collect it by upward displacement, and to keep things safe, an inverted funnel in the water prevents any dangerous backflow. The result? Pure hydrochloric acid ready for use. Next, let's look at nitric acid. Here, sodium nitrate is heated with concentrated sulfuric acid. This gives off nitric acid vapor along with sodium hydrogen sulfate as a byproduct. The vapor is guided through a water-cooled condenser where it transforms into a clear liquid. But here's the catch, nitric acid is sensitive to light, so we store it in dark bottles to keep it stable. In short, sodium nitrate plus sulfuric acid gives sodium hydrogen sulfate plus nitric acid vapor, a straightforward yet precise process. Now for the industrial giant, sulfuric acid, made by the contact process. Step 1. Burn sulfur or roast sulfide ores to form sulfur dioxide. Step 2. Oxidize this sulfur dioxide into sulfur trioxide using vanadium pentoxide as a catalyst at around 450 degrees Celsius. Step 3. Absorb the sulfur trioxide into concentrated sulfuric acid to form oleum, which is then diluted with water to produce sulfuric acid. This multi-step chain is designed for efficiency, allowing industries to produce massive quantities continuously. Equations: SO3 plus H2SO4 gives H2S2O7. H2S2O7 plus H2O gives 2H2SO4. This process is widely used in industry due to its high efficiency and product purity. Bases can be made just as efficiently. Many start from metal oxides reacting with water. Calcium oxide, when combined with water, produces calcium hydroxide, a reaction we call slaking offline. Sodium oxide reacts in a similar way to give sodium hydroxide. These bases are powerful, highly corrosive, and must be handled with care. Another industrial route is the causticization process. Here, sodium carbonate reacts with calcium hydroxide, producing sodium hydroxide and precipitated calcium carbonate. The reaction sodium carbonate plus calcium hydroxide gives sodium hydroxide plus calcium carbonate. The solid calcium carbonate is simply filtered out, leaving us with a clean solution of sodium hydroxide. Finally, we have displacement reactions, where a more reactive metal pushes a less reactive one from its hydroxide. Take zinc and sodium hydroxide, for example. Zinc reacts to form sodium zincate and releases hydrogen gas. This method is also handy for preparing ammonia solution. Just dissolve ammonia gas in water and you have a basic solution ready for various applications. It's chemistry at its most practical and resourceful. Let's quickly summarize the preparation methods for acids and bases. First, acids can be prepared from nonmetals, oxides, salts, or by direct synthesis. Second, hydrochloric acid is obtained by reacting sodium chloride with concentrated sulfuric acid, while nitric acid is prepared from sodium nitrate and concentrated sulfuric acid. Third, sulfuric acid is manufactured industrially through the contact process, which involves oxidation of sulfur dioxide and formation of oleum. Fourth, bases can be produced from metal oxides or carbonates, both of which yield strong hydroxides. And finally, displacement reactions using reactive metals can produce bases or ammonia solutions.